You can have that out and look at it. And we've got things that we'll talk about on your periodic table dealing with what's called periodic trends. And it's just based upon values increasing or decreasing across or down. So in these periodic trends that we take a look at, we're going to look at electron affinity, give you the definition for that. We're going to do electronegativity. We're going to do atomic radii, how big the atom is, and then ionic radii. So those are the 4 trends we'll look at.
Here's $750 from the Kelly boys.
They did all right.
And Avery Kolb sold $420.
I think I got Avery's here.
Yeah. What's the rest of you losers?
Not that.
They didn't sell that. I didn't sell it either.
I've got a check I can make out, but I don't know if I'm going to or not. Okay, electron affinity is basically the ability of an atom to gain electrons. So it'll be a value that you can look at and go, okay, that particular atom wants to gain electrons, and then you can look at another one relative to that one and say, oh, well, this one doesn't gain or won't gain or be less likely to gain an electron. Okay, electronegativity is kind of like electron affinity, but it's in bonding. Okay, so this one's the ability to attract an electron. During bonding. We'll say covalent bonding. Okay, so here, electronegativity, they're bonded. Electrons are bonded. They have a sharing take place. Electron affinity, they haven't bonded yet. So this atom is either going to gain or lose electrons based upon its desire or affinity to pull in an electron. Okay? Atomic radii is just the size of the atom. So radii would mean the distance between the central portion of the atom and the outer portion of the atom. And so it gives you an idea about the size of the atom. And ionic radii is similar, but we're going to look at both. Look at sizes of both cations and anions. Okay? So questions on those. So the first thing we'll look at is electron affinity. Okay, do you guys have a textbook? You want to open up to pages that talk about electron affinity. And electron affinity is measured by how much energy it gives off when it pulls in an electron. So it's measured by differences of energy when it pulls in an electron. And so the page on electron affinity is page 288. 288. the actual definition is given there. It says the energy change associated with an addition of an electron to a gaseous atom. So it's a change of energy that takes place when an atom pulls in an electron. Okay, and then that energy is kind of what we're going to look at. We're going to look at that energy, okay, associated with that. That energy is said to be exothermic, which means it's giving off energy. And the more energy it gives off, then the more likely it is to pull in an electron. So on your chart, okay, I don't think they give electron affinities. Oh, no, they don't. They give you a graph going across for the first 20 elements. Which elements have the highest amount of energy associated with them on page 289? Highest. When we say highest, we mean the highest negative value, because that's how much energy is exiting out. So it's when we take a look at energy, if it's negative, energy is pushed out. Energy is given off. Okay? And when we put a plus with it, energy is going in. Okay? We don't want to put energy. If we put energy in, that means we're doing work to push that electron in. Well, that means it doesn't want an electron. If you have to push and put in work to push in an electron, you're putting in work. Well, that atom doesn't want an electron. If you're getting out a lot of energy, thus high negative number, then it wants an electron. The more energy it gives off, that's better for pulling in an electron. So, which elements have the highest electron affinity then?
Chlorine and fluorine.
Yes. Which one's higher?
Probably chlorine.
Okay. So chlorine and fluorine are the highest. Okay. What's the next highest? Would you say?
Sulfur.
Sulfur? Keep going. What's some others? We're looking at the chart on top of page 289, figure 735. So it looks like sulfur, then what? Carbon, oxygen, silicon. Okay? And we're just taking the top whatever in the first 20. So oxygen, silicon, sulfur. Okay, so when we look at our periodic table, okay, terrible periodic table, by the way. So then we've got hydrogen, we got fluorine and chlorine. Okay, then we've got oxygen and silicon. And what's the other one? Oh no, silicon's over here, and then and sulfur's below oxygen, right? Okay, so where on the chart do they have the highest electron affinities? And I messed up on this because this is supposed to be. Let me redraw that. Messed up. No, people get mad at me because I did it wrong. Okay, let's do this again. Okay, so here is fluorine, chlorine. Then we've got oxygen, sulfur, and then we've got silicon. Right there. Okay? So what area has the highest electron affinities is this area here. Okay? Excluding nitrogen, right, and phosphorus. Excluding the noble gases. Okay? they're desiring an electron more than anything. Okay, so here's electron configuration for neon. We take a look at neon. Here's electron configuration for neon. Do you see why it doesn't want an electron?
It's full.
It's full. All these are full. Okay? Nitrogen's not on our list. So let's look at nitrogen. Let's look at one that doesn't. Nitrogen's not even on there. On our list, nitrogen would be what? Number 7, and it's not even, it has a 0. Nitrogen's a 0. So here's nitrogen. Nitrogen's a 0. It doesn't want one because it's got half-filled ones. And so to put an electron in here, there's resistance to that because that electron will repel that electron. Okay? So it's not going to pull in an electron. So that's why it's 0. What's another one below it that's pretty low? So what's in the same family as nitrogen that's pretty low as well?
What do you mean low? Like, what are we looking at?
We're looking at a value close to 0 or closer to 0. So nitrogen's not even on the list, right?
Oh, are we looking at the chart?
Chart. Yep. Yep, we're just looking at the chart. So nitrogen's not even on the chart, right? It's not on the chart because it's 0. Nitrogen has 0 affinity, no energy. Okay? So what else is close to 0?
Boron, calcium.
Boron, calcium. Okay? So we can list out those ones that have very low affinities. Okay? We've got boron. Okay? Boron's here. And then we got calcium, it's over here. What else is low? Lithium is low. It's here. Hydrogen's low. It's there. Sodium is low. Aluminum's low. Aluminum's below boron, right? Okay. Phosphorus is low. Because phosphorus is same configuration as this. So if it's all full or half full, it does not want electrons. If it's half full or all full, a sublevel, it doesn't want electrons. Okay. So that's affinities. Okay. There's really no pattern for affinities. The only pattern is, and if you look at its electron, so here let's look at chlorine's number 1. And I'll just show the last one. So here's chlorine. Do you see why chlorine's really high? It only needs 1 to be like its idol. Like neon. Okay? Fluorine. Guess what fluorine wants to be like? Neon. Needs 1. Has a high affinity for electrons. It gives off a lot of energy once it gets that electron. Okay? But if it's full or half full, it doesn't want electrons. That is the trend. Okay, that's the trend. If it's half full or all full, when you look at its orbital notation, it doesn't want electrons. Now, if it needs a couple and wants to fill its level, then it's more likely to pull in electrons. Okay. Any questions on electron affinity that you guys have?
Does
Go ahead.
so like for chlorine on
Yep.
that like chart, it's a little lower than fluorine. So like bromine, would it like have a like if it was
Right. So you can look at tables.
Graph.
You can look at table 7.7, and it's not consistent. Table 7.7 down below, where it gives electron affinities for fluorine, chlorine, bromine, and iodine.
yeah.
It generally goes down, but it goes fluorine, and then chlorine goes up, and then bromine goes down, and iodine goes down. So in general, if you go down a column, in general, it has less affinity for electrons. In general. You go across the periodic table, there's really no trend because there's so many places where it's half filled or fully filled, the sub-level, that you're going to have some zeros along the way, or really close to zeros. So the main thing is if it's half full or completely full, an energy level or sub-level, then it's not going to want electrons. If it's really close, if it's really, really close to filling that level, it's more likely to pull in an electron because it gives off more energy. Okay? Any thoughts on that? That one doesn't have a real good trend we can look at. So the first one we look at, really, other than knowing the orbital, you can tell a lot about it, you know, if it's going to be willing to take one in or not. Okay. Electronegativity. That's when it's bonded already. So how likely is it to be close to the, when we take electron affinity, look how close it's going to be to the nucleus when we look at electron affinity. So you guys turn your periodic table over, and you do have electron affinities you can look at. So this has a really good trend, electronegativity. So let's don't go hydrogen helium. Let's take a look at the next two rows going across. What happens to electron affinity going from left to right, excluding the noble gases?
It increases.
It increases. Okay? So electron affinity will increase going across, except for the last group. And everybody knows why that is the case, because they don't form bonds. So they increase in electronegativity going across. Going down decreases. Okay. So I'm going to give you a general reason that's pretty easy to understand. Okay, and only give you a couple examples of that. So when two things bond together and they're sharing electrons, you can kind of see visually why one has a bigger share of electrons than another one does. Okay? So we'll do two extremes. All right? We'll do sodium. Okay? We'll do sodium. It's got 3 levels. Now, I'm not going to do sodium. I want to do 2 nonmetals. So I'm going to do fluorine You guys don't have to show this if you don't want to. Okay, and then we're going to bond it to iodine. Okay? So this is iodine, and they're sharing those two electrons. So the nucleus is what pulls these two electrons in. So the nucleus is in here on these two, and it's pulling in those electrons. So which one are those electrons closer to? Fluorine's nucleus or iodine's nucleus? Fluorine. This distance here between these two are closer. So that means that fluorine has a greater share of those electrons. That's why fluorine's 3.98. Okay, what's iodine?
2.66.
Iodine's 2.66. So it's further away from the source that's pulling those two electrons in. So just like gravity works, nuclear force works the same way. The farther electrons are away, the harder it is to attract those electrons and pull them toward. And so it has less of a share. So that's why iodine's 2.66 and fluorine's 3.98, because those electrons that are being shared are closer to fluorine. That's the one. Now, if they're equal distance to fluorines and their fluorines bonded together, what do we know about the difference in their electronegativity? So this one's 3.98 and this one's 3.98. So what kind of share do they have? Equal share. So now we get into polar and nonpolar when we get into that. Okay? So that would be polar. Alright? That would be polar, and these are nonpolar because they're equal. It'd be a nonpolar bond. Okay? Alright, we're going through pretty quick through this. So we got electron affinity, which means the ability for an atom to pull in an electron, and the higher the negative charge, the more likely it is to pull in an electron. We got electronegativity, which means that if they're bonded together, if it's a high number, it has a strong ability to pull those electrons close to themselves. And so it increases going across and decreases going down. Okay. Atomic radii. Next one, page 286 at the bottom, you're given numbers. Nope, that's not it. That's something else. Page 290 has atomic radii, picometers. What happens to the size of the atom as we go across? Decreases. Atomic radii decreases. Okay, you can actually see it gets smaller. The size of the circles get smaller and smaller as you go across. If you go down, what happens to atomic radii?
It's bigger.
Gets bigger. Okay, everybody knows why it gets bigger going down, right?
There's more.
More levels. More levels are added. Okay? As you go down, you get more levels. So, for example, you go from sodium. There's sodium. And then you go to your next one. What's the next one after sodium?
Potassium.
Potassium. And then, what's the next one after that? Rubidium. and so on and so forth. So yeah, they get bigger because they add on extra levels. Now you go across, they don't do that. So when you go across, they are adding electrons to the same level. So as they go across, they're adding electrons to the same level, which means you got more electrons that the nucleus can pull in, so that's why it gets smaller. So as you go across, it gets smaller because you're adding more electrons and adding more protons, and so you're just creating a bigger charge inside and a bigger charge outside, and opposites attract, and it just gets smaller and smaller because as you add it's like having a gravitational pull that increases in small increments, and then those electrons having the opposite effect and just pulling in more and more and more until it gets to its very end. Okay? So that's the reason, real quick reason why, as you go across. Okay? Alright, the last one that we're going to talk about is called ionization energy. Okay, so the last one we're going to talk about, is ionic radii. We'll talk a little bit about that. And then also include with that, I'm going to have to add on here, ionization energy. We'll talk about. These two are combined. Ionic radii and ionization energy, they're going to be kind of combined, okay, when we talk about them. Okay, going back to our circles that I had drawn out. Nope. Nope. Okay. This electron here on these three, which one do you think will be easier to pull out? Sodiums, potassiums, or rubidiums? Rubidium's easier to pull out. Why?
Because the nucleus has a less attraction, I guess.
Right. Why does it have a less attraction?
It's further away.
Further away. If it's further away, this one's easier to take out. So this one has a lower ionization energy compared to the ones prior to it. Okay? So that's rubidium. Here's cesium. So then we compare it to cesium. Okay? So there's an electron for cesium. Is out here. Now that one's lower, right, than rubidium. And rubidium's lower than potassium, and potassium's lower than sodium. So as you go down, what happens to the ionization energy? So instead of atomic radii here, as we go down, what happens to the ionization energy as we go down?
It decreases.
Yeah, it decreases. So ionization energy decreases. And this is the reason why. Getting farther and farther away from the nucleus. But if we go across, what happens to pulling that electron out?
It gets harder because
It gets
It's closer.
Yeah, it gets closer. So it's the opposite. It gets harder to take out because it gets closer to the sources pulling it in. So ionization energy does what going across?
increases.
Increases. Again, I'm going through this really fast, and most of this is reviewed for you guys because you kind of have an idea what ionization energy is and electron affinity because we've talked about it in the past. Okay, so one last thing. I'm going to wait till tomorrow to do that because I just think this is too much. So just a review. Just review really quick. Electron affinity is the ability for an atom to pull in an electron. It doesn't really have a trend. But what do you look for atoms that want electrons? What do you look for?
One that needs one to complete it.
Yep. An energy level or a sublevel that needs one or two electrons to fulfill a full level or sublevel. Okay, so what do you look for to see that if electrons aren't going to be pulled in? You look for what? So what atoms or groups of elements don't pull in electrons?
They're half or fully.
They're half full
or
or completely full. Half full or completely full. Okay, good. Next then, electronegativity has to do with the ability to attract an electron when they're bonded. So, what type of atoms have a big electronegativity?
Ones
the
that
ones
are
that-
closer to being like full.
Um,
Or am I looking at the wrong
no,
thing?
you're thinking electron affinity.
Yeah.
So, electronegativity, it gets greater going across. What happens to the size of the atom going across?
If it's smaller.
Smaller. Means it can get closer to the nucleus, which means it has a bigger share if it bonds. Going down, what happens to electronegativity? It decreases. Why? Because the atom gets bigger. And there's less of attraction for that electron once it bonds. Atomic radii, we know it gets smaller going across. And we know it gets bigger going down. Ionic radii, when we look at ionic radii, we'll talk a little bit about that. We haven't talked much about ionic radii. We didn't really talk about that today. We'll talk about that tomorrow. In ionization energy, we talked about today. And so ionization energy increases going across and decreases going down, right? Because the electron get closer to the nucleus, it's harder to pull out. So the smaller the atom, it's harder to take out an electron. Okay? So tomorrow, we'll talk about ionic radii, and we'll also talk about PES and what that is. Okay? It's photoelectric effect, and what you do, this is actually a machine that it's called a PES, and it's called Photoelectron Spectroscopy, and it talks a little bit about the energy of electrons within the atom, and we'll talk a little bit about that tomorrow, okay? I'll give you the assignment, but it's due on Wednesday because we're not fully done talking about some of these concepts. So some of this you can answer. Page 299, 112, 114, 116, 120, 121, 124, 133, and 134. Okay, and now we'll have that just due on Wednesday. And then we'll finish up tomorrow. Probably give you guys a review tomorrow. You can start looking at, and then Wednesday, Thursday, I'll be gone on Thursday. Post the answers to the review on. I can post them on Wednesday. You can look at them Wednesday and Thursday. A lot of the test is over electron configurations and quantum numbers and electron, the trends. Okay?